Alright, hi everybody. We're going to go ahead and start talking about your first calculus concept, that's derivatives. For those of you who care, this is take 2 actually. I need one of those clapboards, right? Okay. Anyway, so we're going to go ahead and get this started. Alright, I've got a couple graphs here. We're going to start, first of all, by thinking about some concepts that are important. We've talked about this before. Hopefully you've thought about it before yourself. But here's a line. Okay, this is a line here, and I've got my, these are just indicating my rise and my run. Okay, so this is my change in y, my rise, and my change in x, that's my run. So to find the speed of this line, okay, all I do is I take change in y over change in x. That's often thought of as the slope m. Okay, if this were our time and this were our distance, then this would absolutely be some kind of speed or velocity. Okay, oftentimes we think of this as the velocity. Okay, and when we're talking about lines, then finding the velocity is super simple. It's just the slope, same thing. Okay, so it's the rate of change of y with respect to x. That's one way to think about it. But of course, objects don't move that way. Okay, it's pretty rare that, except in a vacuum, objects are not going to move at a constant rate. Okay, in practice, we have things that speed up and slow down and stop and go backwards. Right, we have things that go up and down and up and down. So we need to look at speed in terms of a realistic function. So if I want to find out what the speed is at that particular moment, the only way I have to do that is by trying to figure out what line that function represents. I don't have a way of finding the slope of a curve at this point. Okay, so instead I run a line through these 2 points because they're close to this point, right? And I find the slope between these 2 points. That's not so bad. Okay. However, it's not great either. Okay. Obviously, it's not the slope at this point. It would be better if I could get the slope between this point and maybe this point, which is a little closer to this first point, and so on and so forth. Let me show you a quick animation that kind of gives you a better sense, because I can't draw this as well as this can do it. This is the derivative at a point. So we're going to start off with 2 points. Okay, I want to find the speed at this point here. So what I'm going to do is I'm going to find the slope of this line. Okay, and you can see here we have a point C and a point C plus H, which is just to the right of C. So this is not a bad way to estimate the slope of this green line. Won't be a bad way to estimate the speed at this point, or the slope at that point. However, as we move this point, the second point, towards the first point, you can see that the estimate of the slope gets better and better and better. As a matter of fact, if we could let these 2 points collapse on each other, we'd be set, and we would have what's called the tangent line, which is that dotted line. Okay, so as we let the second point collapse on the first point, we get closer and closer to this mythical thing called this tangent line, which is going to be our best estimate of the slope of the speed at that point. So that's what we're after when we talk about the derivative. Okay, we're after the slope of that tangent line at that point, and we're going to let C approach the second point approach the first. So we have to just introduce a little bit of notation here. First things first. We're interested in the slope. If this is the point A, okay, this is the point F of A. We're interested in the slope of the line at that point. Okay, I know the page I just looked at used the letter C. We usually will use the letter A. So if I could try to find the slope of whatever tangent line I had here, that'd be good. So what I do, okay, is I run a line through another point that's just a little bigger than A. Okay, it could be less than A, but it doesn't really matter much, frankly. Okay, I'll call that point our arbitrary x, because we love arbitrary x's. So I have f of x and f of A. And the slope between these 2 points is pretty easy, right? It's the rise, which is the difference of these two, f of x minus f of A, over the run, which is x minus A. Now, this is what we call a difference quotient. Okay? If we let the second point, if we let x get smaller and smaller and get closer and closer to A, we're really asking what happens to the limit as x approaches A. So this is our first definition for the derivative. This is the derivative at A. Sweet, right? Okay, we got it. We got a derivative finally. There's another way we can look at this, however. Okay, we can look at this as the letter A, and then we can look at this rather than as a completely other variable. we can look at this as the letter, okay, a plus h, where h is just some positive number, and therefore this is f of a plus h. And what this does is makes this a little bit easier to look at. Now we have the limit as h. So we want a plus h to go towards a. That means we want to let h go to 0, and we have f of a plus h, right, this up here, minus f of a divided by h. These two things are the same. Okay, you can convince yourself of that if you like. They're both slopes. They're just written slightly differently. And what I'm doing is I'm letting the 2 points collapse on each other. I'm saying what happens as the x values collapse on each other. Okay, so here we go. Now we're going to get into it a little bit more formally. So our derivative, this is what I just wrote. Typically we write our derivatives this way. As I said before, another totally valid equivalent way to write it would be as the limit as f of x minus f of a divided by x minus a as x goes to a. Totally valid way of writing derivative. Okay. However, in practice, we usually use this formulation right here with the h going to 0. Okay. Computationally, it becomes a little easier. So as a slope, we can think of it as a slope. M equals the derivative. We can think of it as a velocity. Okay. V of a, velocity at a value a. Okay. Again, same thing. And this idea has a lot of applications. Anytime you're talking about any kind of rate of change of a function at a particular point, this is it. Okay? All right. So a couple things. We have a couple different notations. Notation number 1 is what I call using the primes notation, which was developed by, oh, there goes my cat, which was developed by Isaac Newton. I don't know how he got that M in on there. I don't even know how. There we go. Boom. And the idea here is that the derivative of f at a is denoted using this notation with an f, and it's just like a little prime. So if I'll do it by hand, f, oh, yeah, this doesn't work, f dash a. Okay, the derivative of f at a. Okay, and again, there's 2 ways to write it. Okay, but Newton liked this notation where we go f prime of a. Okay, so that's one way to look at the notation. Okay, the other notation we can use is Leibniz's notation, which comes from this idea that f of x minus f of a over x minus a, and again that's the same as f of a plus h minus f of a over h, same thing. Okay. We look at it as delta y over delta x, change in y over change in x. So he liked using this notation, and so whereas Newton would have said the derivative of f at x, sorry, this is at a, pardon me, is equal to this, Leibniz would have regarded it as x goes to a change in y over change in x, he would use this differential operator thing. So he would say d, the change in y over the change in x, and he would refer to this as the derivative. It's the same exact thing, just different notation. So these are just the same, they mean the same thing, just slightly different notation. Okay, and notice here I've used an x to match an x here, and we'll get into that a little bit later. But basically the prime notation and the dy dx notation. Okay, so let's look at this this function now. Take a look at this video. I'll put the link on the page. This is a fun video to watch about the argument between Newton and Leibniz. Maybe we'll watch some of it in class. It's kind of fun. Anyway, so let's find the derivative of this using this whole idea of what we call the definition of the derivative as the limit as h goes to 0 of f of a plus h. Our number here, we're going to use the number 2, okay, to use an actual number. So I'm going to use 2 plus h minus f of 2 divided by h, and this is going to give us the derivative f prime at 2. Let's go ahead and do it. All right. So first we're going to need a lot of room, but it'll work out. Don't worry. Okay. The nice thing about these limits is they always work out nicely at the end of the day. Okay. So 2 plus h. So we plug 2 plus h into the function. 2 plus h squared minus 8 times 2 plus h plus 9 minus, what happens if I just plug in plain old 2? 2 squared minus 8 times 2 plus 9. And that's all over h. Now notice I can't plug in h right now because it would be 0 over 0. Okay? But let's see what we can do. Let's see if we can simplify the numerator. Okay, so I'm going to get 4 plus 4h minus 16, minus 8h plus 9 minus, okay, we can figure this out. 4 minus 16 is negative 12, plus 9 is negative 3, right? Okay, I think that's right. All over h. Again, we can't plug in h yet, but let's simplify the top some more. The limit as h goes to 0 of, let's see here, so I get 4, that's so 4 plus negative 16 is negative 12, plus 9 is negative 3, minus negative 3 is 0. Good, so these all are gone. All the constant numbers are out of there. And all we're left with on the top is, let's see, 4h minus 8h. Okay, oh, is that right? Yeah, 4h minus, so negative 4h over h. Now, I can't plug in a 0, but notice that I have h over h, and as long as h is not equal to 0, this is legal. And remember, h is approaching 0, it's not equal to 0, so I'm allowed to cancel. So this is simply negative 4. So the derivative, the slope of the tangent line at this point, when x equals 2, is going to be negative 4. Okay? So that means that it's a negative slope, it's a decreasing function at that point. Okay, that's a pretty cool result there. All right, let's use the derivative to find the equation of a tangent line at the point, rather than 3, 6. So we already found 2. Let's find 2 and, was it negative 3, I think. That's all right. 2 and negative 3. Because remember, negative 3 is what happened when I plugged this into the function. Right? Yeah. Okay. So, let's see here. We already know the slope from the previous part was negative 4. That means that if I use my point-slope form, the equation of the line is going to be y minus negative 3 equals negative 4 times x minus 2. Right? I have the point 2, negative 3, and I plug in with a slope of negative 4. Let's check our graph and see if that really makes any sense. Oh, that's not what I want. Grapher. Okay, so our equation is x squared minus 8x plus 9. That's the equation we're looking at. Oh, I'm going to zoom out a little bit. And so I'm looking at the point 2 comma negative 3. So let's see here. So the negative 3 is about here. Yep, that's the point right about there. And I'm going to add a new equation, and let's just see. My new equation is going to be, I'm going to put this equation in. So I'm going to do negative 4 times x minus 2, and I'm moving the 3 to the other side, minus 3. And look at that. At this point right here, we have a tangent line, and we can see that pretty much at this point, it looks pretty much like a tangent line. So the slope of this tangent line represents the speed at this point. Pretty cool. Okay, we can use even these to do exponential functions even. Okay, so estimate, and again we're using the word estimate here, the slope, the derivative at x equals 0. This is pretty powerful stuff, really. Okay, so I'm going to do again the limit as h goes to 0. I always like this h version rather than the x going to a, but that's just me. You can choose whatever you like. And again, I'm going to do f of a, which is, we want 0, plus h minus f of 0 all over h, because I'm looking for this 0 here corresponds with this 0. Okay, we always, no matter what the function is, h always goes to 0. Okay, it just so happens that here I'm looking at 0, so this 0 is here, and this 0 is also here. Okay, let's go ahead and do it. We're going to plug in well, h really, that's all we need here. So limit as h goes to 0 of 2 to the h minus 1 over h. Okay, now this is going to take a little bit of work. We actually need to estimate what happens to this function as h goes to 0, because this doesn't factor nicely. If I plug in a 0 here, I get 0 over 0, but it doesn't factor in any way that's terribly easy to look at. Okay, so instead, I want to pull up my calculator here and try to estimate the value. So I'm going to go 2 to the x minus 1 what happened there? Try this again. 2 to the x minus 1 over x. Graph it, and let's see what happens to this thing as it gets close to 0. Oh, it actually looks pretty nice. It looks like it's going through the number 1. Okay, let's go ahead and zoom in a little bit. Okay, let's make sure we have the right function here. And again, this is not a proof, but we're going to go ahead and try to zoom in a little. So zoom in. Okay. So now, based on our picture here, okay, it's going in a little bit less than 1. Okay, let's look at our table. At 0, we have an error. Okay, so somewhere between 0.5 and 1 is going to be the slope of this function, because the limit of this function as we approach 0 is going to be the same as the derivative of this function at x equals 0. Okay, and we can actually come up with an even better estimate if we set our table steps to like 0.1. And now we see what happens. At 0, it's somewhere around 0.7 roughly. Okay, that's going to be the limit. So we're gonna estimate it at 0.7. Okay, so it looks as though the slope of the line tangent to this graph at x equals 0 is around 0.7. Okay, so we're going to go ahead and give this we're going to pause it here, and we're going to look at the derivative as the function in the next video.